Okay, good morning. So I only have one announcement, and that would be the about the quiz, which will be released today, hopefully by afternoon. Worst case tonight. So that's the only one that I have. If there are no questions, we can actually get into the lecture. So just as another reminder, I'm going to be covering a new topic every lecture. So that means that we're going to jump over some of the stuff that I covered last term, but I'll include a link to last term's topics for those of you who are interested. I recommend actually watching them because these are important topics. When it comes to quizzes, you'll be quizzed only on the material that I present, but it shouldn't end there. Okay. So we were talking about demand paging, which at high level means looking at main memory as a cache for a permanent storage. The topic that we're going to talk about next is basically replacement policies. This is very important. We touched upon this topic when we were talking about generally any cache, you need to have a replacement policy. I postponed this to here. So here are the policies that we talked about: random, first come, first serve, minimum, and least recently used. So let's look at an example of FIFO. I think I'm going to actually jump from this one. So, yep. Basically, what happens here is you have, let's say, the memory capacity is only 3 pages, and then this is your sequence A, B, C, A, B, D, A, D, B, C, B. And every time you bring a page to memory, you put the character there. So at this point, we bring A because A was accessed. Then B was accessed. We bring B to page 2. We bring C to page 3. Then A is accessed. Well, we have A, so this access will be a hit. We will hit in memory. Then B is accessed. B is also in the memory, so we hit. Now D is accessed. We don't have D in memory, so we want to bring D. With first come, first serve, well, you have to evict the one that has been in memory for the longest time, which would be A. So you evict A, you bring D, but you're very unfortunate because next access is actually A. So you have to, excuse me. So you have to bring A again to memory. So here we basically have to bring DNA. Then another access to D, you have it in memory. That's a hit. B, you just evicted it for A, so you have to bring B. And lastly, C. Now, if you count the number of times that you did bring a page from permanent storage to memory, you can just read how many letters you have in this table. 1, 2, 3, 4, 5, 6, 7. So basically 7 misses is what you get with FIFO on this particular sequence. So 7 page faults. Now let's look at min and see how min does the same thing. So the beginning, it's going to be the same because A, B, and C they don't exist. Now A and B will hit. Now comes D, where we want to evict someone. So we have to evict the page that is going to be referenced the furthest in the future. Now, we have A, B, and C cases. Well, A is going to be referenced right after this. So the reference count is 1. B is going to be referenced here, so a reference count 3, and C is going to be referenced here 4. So C is the page that is going to be referenced the furthest in the future. So we evict C and we put D in C's position. So then A, D, B, they all hit. Now C has to come. We have to pick between evicting A, B, and D. There are not much information here because we don't have the sequences in the future. But as long as we know B is going to be referenced right after, so between D and A, you can pick one because we don't have any information. Here we picked A. It didn't matter because again we don't have the future. So we picked between A and D, and this is what you get. So overall 1, 2, 3, 4, 5. So instead of 7 faults, you get 5 faults. A lot better than FIFO. What about LRU? So if you, in this particular example, if you run LRU, it gives you the same result. And that's pretty much what we were expecting because we wanted LRU to kind of approximate min. It does so in this particular example. It doesn't do that all the time. Here is an example where LRU does a different schedule than a min. Let's look at it. So let's run LRU. A, B, and C, they're going to go. Now, next is D. So we're going to see which one was referenced the least in the past, and that would be A. So we will put D in place of A. Then, unfortunately, the next one is A. So then we have to choose between D, B, and C. Well, B, was referenced the furthest in the future. So we're going to evict B. And again, unfortunately, B is the one that is coming next. Now, between A, D, and C, which one was referenced the furthest in the past? That would be C. So we're going to put it in C. And well, next one is C. And you can see the pattern. So basically, we end up getting a page fault on precisely every reference. So the number of page faults is basically the exact number of references. As you can see, we get a page fault on every single access, which is pretty bad. If you run min on this example, you get 1, 2, 3, 4, 5, 6. So 6 page faults with min. Whereas 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 misses with LRU. So the gist of this is to show you that LRU is not precisely min, but again, min is not practical. It requires us to know what's coming in the future, and LRU wants to approximate mean behavior by looking at past. So they're looking at 2 different things, therefore they make different decisions, right? Okay, so next is to understand a very basic concept that you want your memory to have. You want your memory to give you better performance if you give more memory to an application. So you want the rate at which you get page faults to go down as you give an application more memory. So basically increasing the memory size, you should get less page faults, and that's intuitive, right? You want that. Now, the question is, do you get that with different policies? And that's where the interesting anomaly comes in, where you can actually show that with some replacement policies, this simple kind of like a requirement does not hold. So one example is actually first come first serve. So in this example that you're seeing, we're running first come first serve with a memory that has 3 pages. So the size of the memory is 3. We run FIFO. How many page faults do we get? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 page faults for a memory with size 3 running FIFO. Now let's increase the size to 4. So now I have increased the memory size and run FIFO again on the same sequence. So same sequence, same replacement policy, FIFO. The only difference, I have increased the size. And now count number of page faults, that's 10. So 10 page faults compared to 9. So the number of page faults increased as I increased the size of memory. And that's something that it's kind of like an anomaly. You want to get less page faults for an increased sized memory. So with LRU and min, you won't get this. So this depends on your replacement policy. As you just saw in this example with FIFO, you could get this anomaly, but with some other policies you don't. Examples, LRU and min, they well behave. When you increase the size of memory, the number of page faults goes down. Now, another important topic is how are we going to implement LRU? One simple, like a naive implementation that might come to your mind is, well, okay, on each reference, I set a flag that I have referenced this page, and I sort of sort all the pages based on the references that they got. So every time I reference a page in my sorted list, I bring this page to the head because I just referenced it. And every time I want to see which page has gotten a reference the furthest in the past, I can just look at the tail. So the tail of this list would be the page that I have referenced the least, the furthest in the past. Now, this works, right? It does what we actually want it to do. However, there is a big difficulty and challenge with this, and that would be, well, this means that the operating system has to be invoked on every single reference to a page. And this is pretty impractical and expensive because we don't want operating system to wake up on every single page reference. And if that happens, that basically means waking up on every single instruction. And that's just too expensive to do. So we're not going to do that. So how are we going to do this then? A better or more practical, not better, a more practical solution is called clock algorithm. And this is an approximation to LRU. And you have to remember that LRU itself was an approximation to min. So now we're doing 2 approximations. Now, how does clock algorithm work? So the way it works is you have this, you put all the pages in your memory around the clock. And then you have this clock handle. The clock hand points to a page. Every time you have a page fault, the hand ticks once, and then it points to another page. You go to that page, you check if the reference bit of that page in the page table is set. And just a reminder, who was setting these bits? It was hardware. In settings or in systems that hardware does the page walk, if you remember, every time you get a TLB miss, you would come to walk through page table, and when you find your page your page table entry that contains the translation, you set the access bit, telling the operating system later on, which is here, that we're going to check that access bit, that I actually accessed this page, right? And this only happens on the first TLB miss. So it could well be that the hardware accessed this page a lot, but it was just after the first access. Nevertheless, you here in this algorithm, you just check that access bit. If the access bit is 1, this means that this page has been accessed. So you turn it 0. You probably want to also shoot down the TLB entry with regard to this page so that next time it's accessed, hardware comes and sets this bit, right? So you do that as well. And then you tick one more time. You tick until you find a page that doesn't have this access bit set to 1. What that means is you have found a page that was not accessed from the last time you made it 0. So from the last time you made this page access bit to 0, the hardware hasn't come back to make it 1. And what that implies is that this page hasn't been used for a while. And that's the good approximation that you can use to evict this page. You could, there might be other pages that haven't been accessed as well, and they haven't been accessed for longer time in the past, but you cannot afford finding them. As you just saw, it's too expensive. So this is an approximation. So basically, every time you have a page fault, the hand ticks, you check that page access bit. If it is set to 1, then you set it to 0, you shoot down the TLB, and you tick one more time until you find a page that has access bit set to 0, and then you evict that page. So that's how we basically approximate LRU. Now, one thing that you have to remember is the hand is ticking at least once every page fault, right? So the hand is not ticking every access. That's one point. So that's one of the optimizations we did. So we're not doing stuff every time a page is accessed. So we're waiting for a page fault to happen to run our algorithm. Now, if the hand ticks very fast, it means that you're having a lot of page faults, right? If the hand is ticking very slowly, it means that the number of page faults is less, right? That's basically a fact about this. So if you look over time and see the hand is very quickly ticking, this means that you're getting less page faults. And if the hand is just going crazy, that means that you're getting a lot of page faults. One way of looking at clock algorithm is basically a classification problem or a classification method where you're classifying pages into 2 groups, the ones that have been accessed recently and the ones that haven't been accessed recently. So in LRU, you classify pages into so many different classes, which is basically the ones that were accessed exactly last time, 2 times ago, 3 times ago, and so on and so forth. With clock algorithm, you're saying just 2 classes. The ones that have been accessed recently, I don't care, and the ones haven't been accessed for a long time. And then I'm going to choose one victim among those who haven't been accessed in the past. Now you can actually increase this, right? You can have more than 2 groups. You can have 3 groups. You can have 4 groups. You don't need to have only 2 groups. So that's basically the idea behind Nth-chance algorithm. And that the main point of this algorithm is to just give more chances to pages. When the clock hand ticks and you check the accessed bit, and the access bit is set to 0, in the original clock algorithm, you would say, OK, I found you. I'm going to evict you. With Nth-chance algorithm, you're going to give this page another chance. So each page gets n chances for eviction. So the first time that their access bit is 0, you give them 1 yellow card. You say you have n-1 chances. Next time this happens to them, n-2, until they have 0 chances, and then you evict. So the original clock algorithm is one chance algorithm, because everybody has only one chance. The moment they get 0, they're evicted. But then you can again increase that number and give pages more chances. The other thing that you could do is this one actually holds with all variations of clock algorithm, nth chance or 1th chance. What happens if the page that you want to evict has a dirty bit set to 1? So it could be that the page hasn't been accessed for a while, but it's dirty. So let's say at some point you access this page and you wrote something in it, and from then on you haven't been using this. And the clock algorithm or Nth-chance algorithm has found this as a victim. What should you do? So most of these algorithms give this page that has a dirty bit set to 1 another chance. The reason is if you want to evict this page, it's going to be costly, because you have to write it back to the memory before you were able to evict it. So what you could do is when you find such a page, you actually initiate the write back, but then you start searching among others. So you basically say, OK, this was your last chance. I'm going to actually make your dirty bit set to 0, and I'm going to write back whatever is in this page to the storage. But basically that saved your life. I'm going to find another page. So basically giving pages another chance if their dirty bit is set to 1, because of the high cost of evicting a page with the dirty bit set to 1. One other thing to note is that clock algorithm is synchronous, the way that I just described it, meaning that it just runs every time you have a page fault. You don't need to run it this way. You can run the clock algorithm in the background asynchronously with memory accesses. So if you do so, you basically are, you're ahead of time. You don't wait for a page fault to happen to find a victim. So you basically keep a list of victims at every given time, because your clock algorithm is running in the background, and you hold this list. Every time a page within the list is accessed, you can just remove them from the list. This facilitates the page fault handling in the operating system, because if you run it synchronously, then every time a page fault happens, you have to first run your clock algorithm to find a victim, and then initiate the process for, evicting it and then bringing another page. When you run clock algorithm asynchronously, then you always have the victim list, and when page fault happens, you can just right away find your victim and proceed. I'm sorry, I'm just, sweeping some details under the rug, but I trust that you can actually read those. So now the next topic that is important for an operating system. If you remember, we started this the entire chapter on memory management by talking about two things. First one was protection, which we talked about memory address translation, And the second part was memory management, how you allocate memory. So when it comes to memory management, one of the things that we had to talk about was demand paging. Basically, how can we allocate memory between different processes? And then, you know, obviously we might not have enough memory to allocate to every process, and we might have to make a decision on who's going to go to the storage, to the permanent storage, and then when or how they are going to be brought back to memory. Now, the other important topic in this area is basically how much memory do you give each application, right? If you don't do any allocation and just leave that to your replacement policy, let's say all of them are sharing the physical memory, and you're not restricting how much memory goes to each one of the application. What could happen is that if you have an aggressive application in terms of memory usage, if you have one application, one program that uses a lot of pages, so that program, and it uses them very frequently, right? Then that one program, there is a chance that that one program occupies 99 or even 100% of your memory. Because it's aggressive, it just keeps using those memories, and your replacement policy keeps evicting pages from other processes to make a space for this process. Totally possible. So to avoid these situations, you could actually restrict how much memory each application gets. Now, before talking about how you do that or what are the ways of doing it, one important thing is if you do allocate memory to applications, then you have to go modify your replacement policy. Because as I said, the replacement policy just looks for an evict for a victim to evict, right? That's the job of the replacement policy. Now, if you want to restrict memory usage of each application to a certain amount, then your replacement policy should look for victims that belong to the same process, right? You shouldn't be evicting a page belonging to another process to make a space for pages for this process. That should be clear, right? Because if that's the case, no matter what you start with, eventually one process could take over all the memory. But if you go and modify your replacement policy so that it just evicts pages that belong to the same process, then you confine the process to the memory that you have allocated to it. Now, there are different ways of allocating memory. You could go with equal allocation. You can just, say I have 5 applications running, and I can just equally divide my memory between them. That's one way. You could do proportional allocation. You can proportionally allocate. Now, what's the metric for this? So how proportional to what? So it could be proportional to their memory accesses. So if you have one that has a lot of memory accesses, then you can give it more weight. And if you have one that doesn't have much memory accesses, you can give it less weight. But then each one of them will proportionally get their share. You could also think about, these weights coming as an exogenous attribute to processes. Maybe one process is very important to you, so you give it more weight, and another process you give it less weight. That's another way of doing it, which basically is based like priority allocation. So you give priorities to applications, and based on that priority, you decide who gets what. Very often in data center settings, the ones that I've seen, is kind of something in between all of these, right? It's usually a static. So when you launch your application, you give it some memory, but that memory is decided by by the system administrator. So, you know, in settings like Amazon, for example, where you go and, you know, rent a server, you basically are paying for that memory. So when you look at the server that you're buying, it gives you you know, information about the processor, and it also gives you how much memory this has, for instance. And when you buy that package, well, you would expect the operating system, sorry, the data center manager to give you that much memory. So there are different ways of doing this. You can think of different ways. Yeah, so you can also have adaptive or dynamic schemes where you allocate something and then later on you figure out, okay, this application is getting a lot of page faults. That means that it doesn't have enough memory. Let's increase its memory. Or you give an application a lot of memory and you see that for a big window of time, it hasn't had any page faults. That basically means that it's happy with the memory it got, so you can shrink that memory a little bit and see what happens. So it's kind of like a feedback. So you adjust how much memory you give each application. So one thing that could happen in systems very often is the idea or the phenomenon that is called thrashing. And what that is so here in this graph on the x-axis you have the degree of multiprogramming, meaning that how many programs are running at the same time. And on the y-axis I have CPU utilization. Now, as I increase the number of applications that I'm running on my system, usually my CPU utilization goes up. So for those of you who have done, you know, any kind of performance profiling of systems, you usually look at CPU utilization as a metric for how efficiently resources are being used. So if you have CPU utilization of 100, that means that you're fully utilizing your CPU. And that's pretty good, right? Because you're basically getting your money's worth. Now, if you launch one application in your system, you're not going to utilize the CPU that you have 100%. Why? Because your application is going to do a lot of memory, a lot of I/O, and all the time that it's doing memory or I/O or other devices, it's not going to be using the CPU, so CPU won't be utilized. Now, that's where the multitasking and multi-programming and multi-threading comes in, where you basically time share the CPU. When one application is doing memory, you can start running the other one. When one of them is waiting for network, you can run the other one, and so on and so forth. So this is what it shows. As you increase the number of programs, your CPU utilization grows and improves until a certain point. From there, you get this deep degradation in CPU utilization. And this, you can observe it in almost all systems. And the reason for observing such a behavior is precisely because of memory. So at some point, as you increase and increase and increase the number of programs in your system, each one of them requires a certain amount of memory to run, right? Now, the sum of these memories at some point becomes larger than the capacity of your system in terms of memory. So let's say you have 4 GB or 32 GB memory system. And if I sum up the bare minimum memory requirement of all the applications, it's more than that 32 GB. Well, at that point, you start seeing this behavior where the system has to shoot someone out, like evict someone, and then bring someone else in. And this exacerbates as you have more and more applications. Now, you evict one, you start running the other one, and you still don't have memory, you have to evict another one, you have to, and then when you get to this situation when you're starting to do a lot of memory swapping back and forth between the storage and your memory, well, CPU utilization goes down because instead of doing actual computation, you end up doing memory swaps between your memory and storage. So you basically want to be somewhere here, that you have good CPU utilization, but you haven't hit this threshold for thrashing your system. Now, how do you deal with thrashing? First of all, how you detect thrashing, and then how do you respond to that? Well, detecting is kind of like easy. You can just look at how many page faults you're getting constantly. As the number goes up, that means that you have hit that threshold, and now you're thrashing because you keep getting page faults. How can you respond to thrashing? One of the ways that you could deal with it is to just backtrack on this on x-axis. So if you have launched a lot of programs, well, stop launching them and stop running them. So permanently or temporarily put them in a suspended mode. Don't run them. Finish some of the ones that you're running to make a space, and once they're done, bring the swapped ones back to life and start running them. So that's one way to deal with thrashing. Another important topic, which is very related to thrashing, is basically that concept that I just mentioned. I said, if you remember when I was describing thrashing, I said the bare minimum memory requirement of application. What does that exactly mean? What do you mean by bare minimum memory allocation or memory requirement for a process? So to answer that question, look at this graph. This is a real one. So on the x-axis, I have the execution time. So basically, time is going forward. And on the y-axis, I have memory addresses. So these are page numbers. So at any given time, there is a dot here if the application uses, at that particular time, uses those pages. So you get a dot when my application uses a page with this number. Now, if you stare at this picture, you soon realize that there are regions in this picture, kind of like you can actually put a box around them. And this basically, a box like this means that from this point in time until this point in time, I was using these pages almost constantly. Or from this point in time to this point in time, I have been using these pages. So that basically means that I need those pages. When I have been accessing them, this means that I needed them. So looking at this picture, I can certainly say that pages here are not that important. So if you don't, you don't allocate them in physical memory, I should be fine, because I'm barely accessing some of them, right? And I can afford, because they're accessed really rarely, I can afford, bringing them from permanent storage and using them. I don't need to have them in memory. But pages like this that I'm constantly using, I really want them to be in my memory. I don't want to go to permanent storage and bring them every time I access them. So if I have such a figure, at any given time, I can just sum them up, sum the widths of these rectangles, and that gives me that bare minimum that I said, right? If you give me enough memory in terms of size, so that I can have enough memory to save these pages in the memory, bring these pages in memory, then I'd be happy. So I can make progress. because these are the pages that I need, and they are actually in memory, so I can progress. If you don't give me enough memory, so if I have less memory than I need to save these pages, then I will be starting to do that thrashing stuff. So I will have to do a lot of will incur a lot of page faults. Now, how do we? So if I look at hit rate on y-axis and memory allocation on x-axis for any given time, let's say this time, as I increase the memory allocation, I see these hit rate jumps, right? Every single jump here means that I have been given enough memory to have a space for a certain range of memory for myself. So that gives me a big boost in my hit rate. And by the way, so each one of these boxes, we call them a working set. So this is a working set. This is a working set. It means a set of pages that I'm referencing in the same window of time, right? So at each one of these jumps, I am able to bring one of these working sets to memory. That's why I get a bump in my get a jump in my hit rate. Now there are ways to basically sort of track the working set size of each application, and it's pretty straightforward. So the concept of working set, you have to look at a window of time. So because you're looking at addresses that you have accessed in the past window of time. So this delta is basically the window of time that you're interested in. And every time you get an access, you can add that page to your working set. And as you can see, the working set actually changes. So if I'm at time t2, I look at the past references in this window, I see a lot of page 3 and page 4 is being accessed. So my working set is 3 and 4. If I'm at this time and I look back at my references, I see I have reference 1, 2, 5, 6, and 7. So the working set size, as you just saw in the previous slide, is actually changing. So it's not fixed at any given time, it's actually changing. And you can definitely, algorithmically approach this and figure out what your working set size is by just some notion of tracking the references that you've had in the past. Okay. Yeah, this is also important. So this is the last topic when it comes to memory management. After talking about caching and then physical memory allocation, the last topic that you have to take care of when it comes to memory management is the reverse page mapping. So all that we talked about so far were forward page mapping, basically translations from virtual memory, virtual addresses to physical addresses. That was very important. We have to have it. And that's what we had page tables for. But the reverse is also important. So you have to know for each physical page where it's mapped to which virtual pages. Why is this important? The reason it's important is when you do this demand paging, when you evict a physical page back to the storage, you have to go and update your page tables. So you have to go to your page tables and say, okay, this translation is invalid from now on because I have evicted the physical page. So that's why you have to know which page table elements are affected by this eviction. And that's basically the core map, the reverse page mapping. which you have to actually implement. So some operating systems like Linux, for instance, use some of the reserved bits in page table entries for this reverse mapping. Some other operating systems could have their own databases, data structures, handle this in a different way, but it's actually important. So you have to, at any given time, have these two directional, like from virtual to physical and from physical to virtual translations in operating system handy because of the evictions and translations. So that's that. Okay, this was the fastest I actually taught this lecture. I'm glad we're able to now move on to the next topic, which is I/O. Again, a lot of jumping is going to come, unfortunately, but I think it's better to cover more topics than cover each one of them in depth, especially because I have, you know, lectures from last term that I can reference you to look at. Okay, so the next topic that we're gonna look at is I/O subsystem, storage devices. So we looked at CPU, we looked at memory, and next in line is I/O. Because without I/O, our systems are basically, you know, useless. You have brain, but you don't have any, you know, hands and legs and, you know, actuators. So it would be a robot with just the multiprocessor. So nobody will buy this robot. You want your robot to interact with the environment, and that would be the actuators and the devices. And that's basically, when it comes to a computer, those are your I/O devices. That's how you interact with users, getting inputs and providing outputs. So some, you know, the point being here is that, so in this graph I have on the x-axis different devices, and on the y-axis I have their transfer rates, how fast they can transfer data. And as you can see, there is a whole range of devices. So you have devices like keyboard. At the end of this spectrum, they're very slow in how much data they can transfer, which makes sense because, you know, how fast your speed rate, typing speed is. So that's how much you need your keyboard to transfer data. Whereas you have, you know, some PCIe devices at the end of this spectrum where they have to transfer gigabytes of data every second. So you have this whole spectrum of devices with different transfer rates. And as always, we look at these because we as operating system designers have to know about trends in hardware to then come and think about designing software to manage them. What is the goal of the I/O subsystem? Basically, you want it to be general enough to be able to interact with all devices, so that you don't need to, you know, rewrite or write new subsystems every time you have a new device. So you want to somehow treat all your devices with different range and different, you know, different characteristics to be treated the same way by the operating system. And that's pretty much what you see in Unix-like systems. You probably should know by now that operating Linux or Unix-based systems treat all devices as files. So whatever device you have, you can actually find it being mounted in your dev directory with some permission, and then you can actually read or write from it depending on the device. You can open it and you can close it. And that gives you a really clean interface to interact with devices. Now, a lot goes on into what this translates to when it comes to communicating with the device, which is basically what we're gonna look at. So this is basically the interface between the operating system and the user and the operating system and the device. So there are things that you have to actually note when you're dealing with I/O devices. What is your data granularity? Granularity of some devices are byte, like for instance keyboard, right? And some devices are blocks, like your network card or your disk. The other one is access pattern. Can you access data sequentially, or can you also access data randomly anywhere in that file that you're opening, for example? So you probably don't remember tapes. In those, you basically have sequential access only, whereas in disks and SSDs or flash memories, you have random access. Then is the notification mechanism. Are you going to be interrupted every time the device has new data, or you want to pull the device to know when the data is ready? So with devices that are byte accessible, you usually use functions like get and put to communicate with the device byte by byte. For devices that are block accessible, you usually use with that API that we talked about. You open them, you read them, write them, seek somewhere in that device range, memory range. And then you have also a separate category of network devices, because there's kind of like different enough from block and byte devices. So you have worked with sockets in 252, so you probably know about it. And the idea of select and all of that. So it's kind of like a different category when it comes to networking devices. Now, when it comes to timing, you could be blocking. You could have blocking calls. You read from when you call read, you get blocked until your data is ready. You could have non-blocking interfaces where you basically the similar things that you're actually implementing with your mailboxes, when there is a message, you get that message and you continue. If there is no messages, no hard feeling, you continue, you get an error. And then you can have things like asynchronous interfaces where you're like, I don't want to wait on this, and I don't want to move on, but I need this data, but I have also other work to do. So bring me the data, and whenever it's ready, just tell me. In the meantime, I'm going to do some other stuff. So which is different than these two. So tell me later interfaces. Now, moving on. So by now you should actually know the difference between polling, interrupt driven, and a hybrid mode. So polling is simple, and if you have frequent interactions with device, it would have low overhead. So CPU would just not be interrupted frequently. It would do the job and then get done. But in many cases, if you have infrequent requests from I/O or to I/O, then polling is wasteful. Now interrupts are better in terms of wasting CPU time, because you're actually doing some other work, and when it's ready, you get an interrupt. The bad thing about them is if the requests are frequent, then you're going to be frequently interrupted, and on each interrupt you might actually have to do a context switching, so there's an overhead. So depending on that, and then there is also a hybrid model, which is usually used for networking devices, where you could say, just interrupt me for the first package that is delivered, and from there on, when the first package comes, I know that further packages are going to come, so I can pull. So it's kind of like a combo of interrupts and polling. Now this figure shows a very common architecture for modern computers. It's actually changing these days a lot faster than it was before. But for a while, this was indeed how many systems dealt with devices. I'll tell you more about what is changing. So by just looking at this, so you had the CPU sitting as the commander, and then you had really, really fast interconnect that you had CPU connected to the memory. So this microcontroller here is called Northbridge or memory controller. So which connects CPU to memory. We kind of talked about memory controller. Usually GPU is also connected to this one because GPU also does a lot of, if it is just used for video, then you're, reading buffers from memory and then displaying them into the display, and it requires a lot of memory bandwidth. So kind of like similar to CPU, you have really high-speed connections connecting your GPU to your memory controller. Now, there comes the Southbridge, which is called I/O controller. Usually, again, in past days, it had its own microcontroller. So each one of these had their own microcontroller. That's one of the things that is changing these days, which I will explain. So you had this I/O controller, or the Southbridge, or I/O controller hub, that would be connected to the Northbridge with an internal bus. But then every single I/O devices would be connected to this I/O bus. Now, as you can see, CPU still can, communicate with these devices, but it has to go through two hubs to get to the devices. So these are kind of like, usually this would be off-chip. Back in days, this was also off-chip. Now, one of the things that is changing, and actually changed, this one happened a lot, like way ago. And I think AMD did that first. They brought this Northbridge into the chip, into the CPU chip. So instead of having it as a separate microcontroller outside the chip, they brought this inside the chip, and that gave them a huge performance boost, because if this hub is inside the chip, you can actually go to memory a lot faster than if you were to get out of the CPU chip, go to another microcontroller, and then go to memory. So that was one performance boost they got. Recently, when I say recently, probably a few years ago, AMD brought this Southbridge also on the same chip, and that gave them a huge performance boost. Because if you remember, I showed you the rate at which I/O devices are improving is faster than the rate at which memory is improving in terms of performance. There is still a huge difference between memory speed and I/O speed. Memory is much faster, but it's growing with a lower rate than I/O. But at some point, I/O will catch up, probably, right? If we're stick to the current trend. Now, some of the applications are seeing that the bottleneck is basically I/O. They're doing a lot of I/O, and I/O becomes the bottleneck. Now, if you move this part to the same chip, so your Southbridge is also inside your chip, your I/O controller is also in the chip, then your CPU can access these devices a lot faster. So that's another thing that is changing. The other thing that technology is changing is about these buses. So they also could become the bottleneck in terms of how fast they can transfer data. So nowadays, like you have PCIe, we started with PCI, then PCIe. Now different versions of PCIe are coming, PCIe 4, PCIe 5, PCIe 6. I think PCIe 6, if I'm not mistaken. Yeah, I don't know if there is any devices with it, but the protocol at least is standardized. Yeah, so that's pretty much it in this slide. Now, a couple of slides I have on PCIe evolution over time. I'm going to actually jump. I will link to the discussion I had about them from last term. It was an interesting discussion on how they actually evolved. The main point of PCIe that has made them such a great communication medium is the way they're actually using backward compatibility. So going from PCI without that E to now PCIe 4 or 5 or 6, they're all backwards compatible. So you can, if you have a device that works with PCI, you can actually connect it to PCIe 4 and it would still work. It wouldn't give you the the highest features that PCIe Express 4 or 5 is supporting, but it works. So at least it works. So they kept it backward compatible, and that's such a great thing in terms of design. So whoever designed it back in then, the design was capable enough to hold itself after like decades of usage. They added definitely new features, but this, I mean, it requires both a great design at the first time and then a great team of engineers trying to maintain this backward compatibility, right? Both ways. So in the past, they had to have a really great design that was futuristic, and then nowadays, as engineers are evolving the technology, they also have to have ways to keep it backward compatible. Now, another great thing that PCIe does is that it actually treats devices as individual hubs, and it kind of creates this. The concept is very similar to networks. When you have a network of computers, how it happens, like you have a switch. Each computer sends packets to the switch sends them to a router, and the router routes them to wherever they have to go. They actually implemented similar concepts in PCIe. So it's basically every two device is an endpoint. So that's where you have the PCIe endpoint. Then multiple endpoints are connected to a switch. And then multiple switches are connected to this root complex, which is kind of like a main line that connects every switch to each other. You could have these, PCIe bridge to PCI or PCIX, or you can have different bridges to bridge from PCIe to other technologies. Now, each one of these PCIe devices can send packets to every other endpoint. Now, one of the endpoint is CPU, another endpoint is memory, because both of them are connected to this root complex, and so is every other device. So this gives great flexibility when it comes to communication between devices, and between devices and CPU, between devices and memory, and so on and so forth. So now, when you come to the device, so if a device is PCIe Express compatible, if it can get connected to any of these endpoints, that basically means that the device has to implement a PCIe interface. So it has to know the communication protocol that is used in PCIe. So the device has to have a PCIe interface. And behind that interface sits a hardware controller usually, or bunch of controllers. So these controllers are in charge of the device, and they understand, all the things that the device does. And then through this PCIe interface, they communicate with the rest of the system. Now, what are the things that usually you can find in devices? So we're talking about device controller. So usually devices have set of registers that are used for controlling the device. So if the CPU, for instance, reads or writes to these registers, that implies something. So to give you an example, you can look at the timers. Of course, they're not PCIe devices. They're actually on the same chip as the CPU, but similar concept, right? The timers, they have registers, and by writing into those registers, we kind of configure the timers. If you think about like the project that you're doing, the A9 timer, like it has a register that you can write to, and that identifies, you know, the speed at which the timer should tick, or whether or not it has to raise interrupt or not. So these are registers inside the hardware that we're communicating with, right? Again, it's not a PCIe device. It's an on-chip device, the timer. But again, the same concept. The other thing that you usually find in devices is kind of like is buffers, not just single registers for commands. You could get buffers. For instance, if you have a display, you might have an internal buffer for what is going to be, you know, displayed. So there are buffers that the CPU can write to. It could be a command buffer. Maybe you tell the display to, you know, display a point and then connect this point to another point and another point to another point. So you're giving commands on what has to be displayed, or if it is a data buffer, you just put a bunch of stuff that tells the display, for instance, what to be shown at any single pixel. So both of them. So you might have data or command queues inside your device. Now, specific to PCIe devices or PCI devices, one example would be the configuration space registers. So these are the registers that initially, when you turn on your computer, the device has some pre-configured values in those. When during the boot time, either during the BIOS time or when the operating system is booting, usually it's during the BIOS time, the device communicates with the system and tells the system what it requires, like what range of memory, like how big each buffer is, how many registers it has, right? These information are for PCIe devices. You can find them in this space registers. So when the system is booted, these informations are read from those registers. When the system allocates physical memory, which is basically the binding between physical memory and the device, meaning that you want now, if the CPU wants to read these registers, it just reads those memory addresses. So there is a mapping between physical memory to these registers. Very similar concept that we had, mapping between physical memory and virtual memory. So we mapped virtual addresses to physical memory. Now we're mapping registers to physical memory. So this mapping happens. At that time, the CPU writes to these configuration space registers, basically telling the device that you got this range of physical memory. Now, because the device is actually on the same path to memory, so it can observe the reads and writes that are coming to memory for a certain address range. Now, if I know that those address ranges are assigned to me during the system initialization, I can know that CPU is actually talking to me, not the memory. So that's a great way of basically setting up the device. So during the system initialization, the device first says, oh, I need this many buffers and these many registers, map physical memory to me. Then the system does that mapping and then writes to those same registers, telling the device, okay, now you have a physical memory range. Remember, this is your range. Basically, usually you just get a base address because you know your range, you know how much memory you need. The system just tells you, here's your base. Now, for whatever you asked for, just add it to that base, and that would be your memory because it's usually contiguous. And then that's it, right? Now, every time CPU writes or reads to those addresses, the device knows those addresses are assigned to that device, so it just reads those or gets those messages and responds to them, just using these registers. How much time do I have? Only 8 minutes. Okay. Keep going. Now, here comes the access part. So the one that I just described with PCIe devices is basically memory mapped. So as I said, you just map certain physical memory ranges to your device, and your device will just, listen to those. So every time CPU wants to communicate with the device, it just uses load and store, and the device, because it knows its range, it just responds. Another way that happens, usually with microcontrollers, very often with Intel microcontrollers, is port map. So basically, instead of connecting the I/O device to the same memory bus between CPU and memory, you create a separate bus, which is I/O bus, and then the I/O devices are connected to that I/O bus. So you have two separate buses, one for memory, one for I/O. Now, this means that CPU cannot use load and store because load and store just goes on the memory bus. So we have to have separate instructions for the CPU to talk to the device, and that's where the in and out instructions come into place. So every time the CPU wants to talk to the I/O, instead of using load and store, it uses in and out. But then in and out, they would get separate addresses for the device, right? Because these are two separate lanes, one for memory and one for I/O. So you could have the same address. If it's sent on the I/O bus, it basically means talking to an I/O device. If it's sent on the memory bus, it basically indicates a memory location. Here is an example. I'm going to actually move on from this. It basically shows an example where we map a bunch of registers from the display, and then the display memory, and then graphics command. So each one of them is mapped to different ranges, and then just a bunch of examples how the CPU can communicate with the device. I'm going to jump over. So we talked about direct memory access, DMA, at the beginning of the term, if you remember, which was kind of like a way for us to save CPU time. So instead of the CPU transferring every byte between CPU and the memory, we have a DMA engine. The CPU tells the DMA engine to transfer a certain amount of bytes from this address to that address, and then this happens while CPU is doing some other stuff. The data is transferred between the device and memory, and then once the data is there, an interrupt is raised, and then the CPU gets to know that the transfer is over. So that's the DMA. And you can compare DMA with programmed I/O, which is basically byte by byte transfer of data by the processor. So these are the two that we kind of talked about: direct memory access and programmed I/O. Now, one thing about DMA for PCIe devices that you have to pay attention to is the difference between old devices and then PCIe. So with PCIe, as I said, each endpoint can communicate with other endpoints. So you don't have a DMA engine, a single DMA engine for all endpoints. So instead, each endpoint has to implement its own DMA engine because it can't talk to anybody else and it's connected to the memory. So usually every single device has one or two or even more DMA engines. So they're implemented inside the device. Now, CPU talks to the device, to the DMA engine of the device. Let's say you have a driver, right? The driver runs and programs the DMA engine inside the PCIe device and then sends the command to start. Then the DMA engine inside the device, it's an endpoint. It's connected to everywhere, including memory. So it can start communicating between itself and the memory to transfer data to the memory. And once it's done, it raises an interrupt telling the CPU that I'm done. You can move on. So again, the difference here is that you don't have a single DMA engine. Back in days, each device had one or two DMA engines that would take care of all the I/O devices. Nowadays, with PCIe and even other technologies, other buses, each device has its own DMA engine. So you get a ton of DMA engines in your system. So you don't have a bottleneck of one engine having to serve all the devices. The other topic that is very interesting, and this is actually recent development in operating systems, and when I say recent, probably decade or 2 decades, but is the idea of memory protection, right? So we talked about memory protection when we were talking about virtual to physical memory translation. Now that we're mapping devices to memory, do you need protection as well? Now, many systems, they don't have protection for devices. They're assuming that the devices are well behaved. And usually devices in those systems actually know the physical memory and they communicate using physical addresses because they know their base and they can communicate. Now, this is challenging as different manufacturers produce different devices. So some devices could be malicious, right? And they could, in the background, read certain memory locations and do certain things. They can, if you have a PCIe system, each device has access to every other device. They can send messages to every other PCIe device. So you kind of have a security vulnerability, right? This motivated system designers to think about adding a similar component like MMU. So if you remember what this MMU was, this memory management unit was in charge of address translation. So CPU would spit out virtual memory. It would go to MMU. MMU had access to the page tables, and it would turn it to physical memory. So every process would be isolated because they wouldn't see the physical memory range. Now, you could get the same thing by adding an I/O memory management unit. Exact same concept, right? This here sits between the I/O hub and the memory hub. Here it gets ranges for registers and buses, but then it translates them to physical. So basically sort of giving the devices a virtual range instead of actually giving them physical range, and then doing the translation for them. That way, you could think of it as the example I said during the initialization when the device says, I need this range. Instead of giving the device its base address in physical memory, you can give it a base address in virtual memory and give it another, also the bound. Now, every time the device wants to communicate with memory, you just translate. And every time you want to send, like a CPU comes and sends data to the device, you can do the translation as well, right? I guess from CPU to this, you don't really need the translation. You can actually use the virtual address that the CPU produces. But going back from the device to memory, you can use the translation. Now, this is kind of cool. It gives you the isolation and security that you need. There is one difficulty when it comes to PCIe devices, and that's the fact that PCIe devices can bypass this guy, because PCIe devices are connected to each other as well. So they can communicate with each other without going to this IOMMU, right? They don't need to go there to communicate at least with each other. So to get rid of this, you can actually enable you can enable ATS service in your PCIe device. Sorry, you can disable this, because when it's enabled, you can bypass IOMMU, but you can actually disable it. The other problem with this is another interesting topic in PCIe. So very similar to TLB. So what was TLB? TLB was the idea of having a cache for address translations. So if I go through MMU once to translate, I don't want to go next time as well. I want to cache that translation in my TLB. The exact same idea works with PCIe devices. So if they go through IOMMU once, they don't want to go through IOMMU n times. They when they know their translation, the translated address, they want to use that translation. They don't want to spend time in translating. So for that, now that each device has its own DMA engine, they could also have their own cache as well. So each device has its own TLB of sort. Now they could claim to the IOMMU that, oh, I don't need your help. I have translated this in the past, and here is the certificate. This is the translation. You don't need to be involved. I have the translation. But they could be lying, right? The device could lie that, oh, I know the translation, and they actually are malicious, and they just want to read a physical address. So it's not always performance. It could be some malicious behavior to read data. Oh, I'm 4 minutes over time. Sorry. Let me finish this slide and I'll be done. So both of these two could be disabled to solve the problem, security problem. So you can actually use access control service, ACS, which would then disable ATS, which is the problem number 1. Where's my mouse? Yeah, so if you use ACS, it can disable ATS, and it can also require every single PCIe packet to go through IOMMU. So basically telling everyone you cannot cache translation. That has a great impact on performance, but at least it brings in security because then everybody has to go through IOMMU and they can't cheat the system. Okay, so that's pretty much it. Hopefully next lecture I can finish memory. I'm gonna again jump, but hopefully I can stick to every lecture giving you a new topic. So we'll see how it goes. Thank you for those of you who attended the lecture today, and thank you for those of you who are going to watch this lecture. Please, if you haven't evaluated the course, do so right now. Thank you. Take care. Be safe. Talk to you later. Bye-bye.